All right, hey guys. All right, hey guys, and welcome back to another AP Physics C video. Today we're going to be doing the electric potential on a line of charge centered on the y-axis. So, yeah, this is going to be just one of those quick derivations, a little bit easier. They didn't give us the length, but we know that this length, right? Oh, I should say, let's just hop right into it. So we didn't get length, but we can read off of this graph that it's about 2L. So we're going to think again, like we did last time. And you don't have to follow this process each time, like splitting it into a conceptual thing, but I find that some people prefer to do it that way. That's actually how I learned it the first time. And we're going to visualize that little dy that corresponds to a dq, right? And that little dq at that point will produce a small voltage dv. So in order to compute that dv, we know that the voltage from a point charge is kq over r. But we know that v, or the little dv that we want, is produced by a little dq over r. And like last time, again, we need to define our r in order so that it's in terms of yp and our integration, or well, and the variable we're integrating with respect to. So like the other time, we know that dy is going to vary, right, with different distances y along this entire span from 0 to 2L. So therefore, how far away, sorry, not therefore. So now we need to think about how far away would this distance be from dy to yp. In other words, the radius, what would that be in terms of yp and y? Well, if you can see, that yp is this, I should do it in a different color. That yp is this entire distance, right? But we know that we have this little small distance y. So if I take yp and I take out that little chunk y, oh, well, guess what? The radius will just be whatever's left up here. So therefore, when I said take out, radius is really yp minus y, right? Because y will vary from 0 to 2L. So like it's really sometimes difficult to understand that path of the integral that it will take from like 0 to the integration bound, or like lower bound to upper bound. That's how the variable will literally vary. So yeah, that's our r, and we'll just keep that in the back of our head for when we actually will sub in later. So now I'm going to sum up all of those little dv's and all of these for all these little dq's. And now I will get V, and I don't need an I hat or J hat this time, or a R hat, because voltage is a scalar. I'll get V equals K, integral dq over r. And this is an equation on your equation sheet. And now we could have just started from here. I just want you guys to see the derivation again. But now we need to think, well, from where to where are we integrating r from? And like I said earlier, it's going to be from 0 to 2L, because that's the way we defined our r. Because when r is 0, right, the distance from that little, let's say our dy is like here, right? And the y would be 0. Well, the distance would just be yp because it's at the bottom end. But if our dy was up here, which it will be once we compute the integral, like which it will be at some point, right? If our dy was up here and the y is 2L, well, the distance will be yp minus 2L, which checks out according to our r equation. So now we're just going to sub in that r equation with our bounds of integration. It'll be from 0 to 2L dq over yp minus y. And now you might be thinking, well, I have y, which will vary, I know, as the integral proceeds from 0 to 2L, but I have dq. Shouldn't I have dy? That's exactly what you're supposed to think. So now we're going to get to dy using lambda. And I know lambda, every object that has charge and length, so long as it's linear, right, and it doesn't have like surface charge, it will have a linear charge density, which will be dq dy. And like I said in the last video, it could be dq dx, dq dr, dq dl. But in this instance, charge is varying along the y-axis, not the x-axis, right? So there's only charge on the y-axis, so it's going to be dq dy. So now, what they showed me earlier, well, what I should have said earlier is uniform. This rod has uniform charge density. density. And that allows me to say that lambda is equal to Q over L. Okay, so now that we know that, we can say that lambda times dy is equal to dq. And now I can sub that into my integral and say that the voltage, or the electric potential, is equal to K integral from 0 to 2L 1 over yp minus y lambda times dy, right? And now I'll just move that lambda because it's a constant out, and I'll get 0 to 2L 1 over yp minus y dy. And now I could very well do a u substitution here. I'm going to not, because I know that a property of calculus is when I integrate a function that looks like 1 over ax plus b dx, the integral will be 1 over a ln ax plus b plus c, right? So really, all I'm going to do is identify, well, what is the coefficient to my variable, right? Because I'm integrating with respect to dx, and there's x here. Well, here I'm integrating with respect to y, and there's y here. What's the coefficient to y? Well, it's -1. So I know that this integral will compute to k lambda. It'll be 1 over, and what's the coefficient? -1 times ln yp minus y. And now I just bypass the u substitution by knowing that fact from the bounds of 0 to 2L. And that's a lot easier, isn't it? So now I should move this to like up here, and then draw arrows to show what I did with it. So now I don't really want to have that negative on the outside, right? It's really up to preference. If you keep it on the outside, your equation will still be right. But just because I feel like it, I'm going to put that negative into the equation by applying it to the bounds of integration. So if you have a negative, you're allowed to switch your bounds of integration. The bounds of integration, when you switch them, will kind of just absorb the negative. So now this will be from 0 to 2L. And now I will get k lambda ln, and now I'll sub in, well, yp minus 0 is just yp minus ln, okay, yp minus 2l. And now if you remember, when you have logs that are being subtracted, ln a minus, I'm running out of space here, ln b is equal to ln a divided by b. We're just going to do the same thing here. K lambda, oh, that's a bad lambda, k lambda ln, and we're going to have yp all divided by yp minus 2l. But if you saw earlier, our lambda, we're given charge q. So we really just want to express this in terms of q. So it's going to be kq over, and what was the length? Well, the length was 2l, because here I put, where was it? Here I put q over l, but the l is actually, the length is 2l. So kq over 2l times ln yp over yp minus 2l is equal to the voltage, or the electric potential. So hopefully that helped and made some more sense. But yeah, if I missed anything, or if you guys want me to explain something further, let me know. But for now, I'll catch you guys in the next video, and thank you guys for watching.